So just to follow on, before we get started, just kind of want to follow on Cindy's last point about expanse accounts. Can I get a show of hands of who does not yet have an expanse account on on the system? We got at least one, two, four, five. Okay. One clap. Okay, so maybe that's a six. um, Okay, it looks about five or six folks still don't have accounts today. Yeah, I would definitely recommend. I'm sure Cindy's going to post that in the chat. The links to where to. Is it through email, Cindy, again that you want them to do that, or yeah, follow the instructions on the GitHub?
Yeah, the GitHub, but I also, on the email reminder for today, I noted how to start off with getting the seed account, and then there's a link to the repo as well to go to the next steps.
Okay, great.
Yeah.
Yeah, so yeah, for those of you who don't have accounts yet, you won't necessarily be able to follow along today, but I suspect over the next few weeks, there'll be a lot of hands-on examples that you'll be able to run on the system. So I'm assuming that most people will have access to the system today. So you unfortunately won't be able to follow along, but all the code and stuff is on the GitHub for the training series, so you can definitely come back and run them later when you have time and when you have access to the system. Okay, great. So at least the majority of people have accounts on the system today. So this is session 2 of week 2 of session 2, week 10 in the series. If you didn't join us for the first half of the training series, it was mostly focused on more non-programmer focused HPC and cyber infrastructure topics. This is kind of a new format for us this year. Originally, in past years, it's sort of been one long training series, all, I don't know, 14 weeks or so that I think we do. The idea this year was to break it up into a sort of non-programmer set of topics in the first half and a more programming focused set in the second half. So that's kind of the idea for today's talks. The original title was Introduction to OpenMP and Threads, which we will discuss. However, if you were here for the first session, week 2 there was a parallel programming concepts talk by Bob Sigwitz, our director of education. Really sort of giving you some key definitions and ideas about why parallel computing is important for different problems, and some of the general techniques and things that are used from a high level sort of non-programmer perspective. Today, I'm kind of trying to actually mirror that a bit with the topic of OpenMP and threads included. The reason for this, I didn't really want to go down into just a straight OpenMP talk. Is, if you're familiar with it a little bit, it's sort of a framework for a programming API framework, sort of directive-based framework for C and Fortran codes only, really. And I don't know, I was kind of assuming most people aren't necessarily C or Fortran programmers. Maybe people do have some C programming experience. So I kind of wanted to broaden things out a bit from there to get us kicked off with the parallel programming aspects of this second half of the training series, because for the next few weeks, you'll be seeing more essentially parallel programming frameworks. So next week, I think Mahidar, who just joined us, will be talking about MPI, which is for distributed parallel programming across nodes. So today is really going to be focused on parallel programming, running applications on a single compute node or a few cores on a single compute node on Expanse. But then I think we have one of our GPU experts, Andy, is going to talk about GPU programming. And so there's going to be a lot of ideas of just in general parallel programming, but in different aspects and facets of how you can go down the rabbit hole of learning parallel programming if you're not familiar with it. So this is really to this talk is really to kick that off and get you set up and ready to run some of these example jobs. You could spend a whole semester learning just OpenMP and shared memory programming, which is kind of what we're talking about today. But this is really just to get your feet wet, give you a few different ideas and sort of the practical things you'll need to know how to do on Expanse for the next couple of weeks, and with some of these other talks as well. Okay, so with that sort of caveat on sort of the frame for today, this is the kind of what I'm hoping you'll get out, the goals for today. So sort of review these basic parallel programming, parallel computing concepts that was discussed in the first half of the training series. For those of you who are new to the training series, get you up and running on Expanse, or if you were here for the first session and just didn't get comfortable with running on Expanse or haven't done it yet, this is a good opportunity to do that today with today's examples. Because I'm really only going to have a few slides on sort of the concepts, and then we'll jump right into sort of learning by example on a few of these things. And one of the first examples we'll do is just an embarrassingly parallel problem, and what what that is when you're running on Expanse and how that might help you in your work or with different project you might have. And then get into this thread-based or shared memory parallel programming model with both examples from OpenMP, and also I have some Python examples. So I figured a lot of people would probably be more familiar with Python, and so they have a threading library that we'll play around with today, and it'll teach you some of the concepts that will be useful both for if you're really interested in OpenMP programming. I think it's a good learning framework as well. You'll see so I'll just open this up on the second slide here. I'll probably be switching back and forth between the web and my slides. Let me get this kind of stuff out of the way real quick. And yeah, if Cindy or Mahi, if there's any questions along the way that you think we should stop, just let me know if I'm not monitoring the chat. Yeah. So for those of you that missed this talk in the first half of the session, this is the one, as I mentioned, Bob Sinkovitz. You can find the slides there for a more in-depth sort of discussion of some of the things I'll just go over quickly here. And in week 2, the slides are available. Oh, that's the Expanse overview. You can learn about Expanse and that says slides, but this is the talk that I'm referring to. This is kind of sort of the part 2, I would say, on sort of the programming front. So you can find the slides here on the repo later if you haven't seen the talk. Okay, so let's go ahead and get started. I'll go to full screen for a bit, I think. So when we're talking about parallel programming, right? Well, what are we trying to do? Well, we're starting usually from, you have a problem that you've written a program with sort of in this sort of traditional serial computation mode, right? So you have some problem that you've programmed with some set of instructions, and those instructions are just fed to your computer processor one by one after another, with the data being shuffled around from memory to disk sometimes, or to back to the processor. This is serial computation. Everything just flows in a linear progression of the instructions being executed on a single processor, right? In parallel computation, right, you're going to take, say, that same problem and break it up into, again, a series of instructions, but you want to be able to do that work across multiple processors. And so, for example, one of the simplest things is if that problem, say in this schematic, you can think about these divisions of the problem into, say, 4 sections to run on the 4 processor cores we might have access to. You can think about, like, the instructions are all the same running on each processor, but each one is fed slightly different data, right? So that's one way to think about parallel computation. This is what we would call, if there's no sort of dependency on the data that you've broken up the problem into these 4 quadrants, that would be a embarrassingly parallel problem, where essentially each individual small problem that we've sliced that big problem up into is can be run independently with the same set of instructions on each processor. It doesn't really matter how many processors we have or how big the problem is. It's just you divide it by the number of compute elements, these processors you have, and you can just carve up the data. There's no dependencies between instructions from one processor to the other that matter. It's just sort of straight, embarrassingly parallel computation. We'll do an example of that. I'll show you sort of just one feature of running jobs on Expanse where you can sort of implement this in a relatively simple way, in a simple example. Where things get more tricky in parallel programming is when the instructions between those different processors, say, have to communicate with each other, right? So we'll see today there's some issues about when you're doing this on, say, one of the Expanse nodes with OpenMP or with Python today, right? Today we're really talking about this, what's called a shared memory parallel programming model, where basically sometimes the instructions in these different pipelines here are pointing at the same data in memory, right? And so they need access to, say, the same variable, each of them. And maybe those instructions on the different processors are updating that same part of memory in your calculation. And you have to be careful. You can imagine if there's different CPUs pointing at the same data, trying to modify the same place in memory, things can get complicated. You have to be aware of what the different instructions running on different processors are doing to the data that's shared in memory. So that's what we call it, a shared memory sort of model. So just simply, I'm sure you can imagine sort of what are the reasons to go parallel. I just give you kind of the three, I think, big ones that most problems fit into. The first is you want to solve your problem more quickly, right? And so this is sort of a weather simulation from, I think, 2005. This is the National Weather Service, like Hurricane Katrina, like forecast model from 2005. I think it's a snapshot of that. And right, you can imagine this type of problem is something you want to do more quickly, right? When you have a hurricane coming towards a city, you need to project where it's going to make landfall, and you have to turn around those projections, maybe a couple times a day, and you have to do it quickly with, sufficient accuracy. But in this case, you're really just trying to do it as fast as possible with the best accuracy you can in the time that's needed to make the predictions, right? So there's sort of these sometimes real world problems where you have time constraints. You have to turn around this calculation by midnight so that you can update the forecast for the next day, something like that, right? The next kind of reason you would take your problem, say your serial problem, and go parallel is you want to scale up the size of the problem. You might want to include more complex dynamics or, say, physics, if it's like a physics-based model, such as like this weather simulation, and you want to solve that problem with higher fidelity. So, right, these two images actually came, I think, from some National Weather Service article that I was when I was originally putting this talk together, where they showed a comparison. I think this was like a 2015 update of the same model of Hurricane Katrina, of how much more detail they've been able to add to the same sort of simulation over that 10 years later or something like that, or where essentially, right, the computing power was sufficient to, say, solve the same problem in the same amount of time, but with much greater complexity and higher fidelity sort of simulation, right? 10 years after the fact. So that's one. It's a nice example, I think, of kind of this trade-off between speed and scale, right? So they didn't have the computational power 10 years earlier to have as good of a simulation or as accurate, as complex, but there's reasons to go to that higher complexity, higher fidelity sort of models, if you can, in certain cases, for your science or engineering problems. Another one, which is more related to this embarrassingly parallel problem, is like you just have a throughput problem, essentially, where you have, say, lots of data, or you need to run very many versions of the same simulation over and over again with just slightly different parameters, or maybe there's some randomization in the problem. This is an image from the IceCube collaboration. This is a neutrino detector at the South Pole. So it's detecting these elementary particles from astrophysical sources. They have this big block of ice that they can have detectors in. It's what all these little balls are, or detectors lighting up when they detect a particle in the ice. And one of their computational challenges is modeling the clarity and the propagation of light through this big, I think it's like a square. It's called IceCube because I think it's basically a 1 kilometer by 1 kilometer block of ice that they have these detectors monitoring essentially. And they run a lot of Monte Carlo simulations to understand the propagation of through the ice. Obviously, it's not like a perfect, ice cube. It's, it's a natural layer of ice that they have to sort of model and take account of defects and different issues that they can see in the ice to model what the propagation of the detection of the light from the particle interactions in the ice mean in terms of their overall measurements, right? So they use a lot of GPUs. Basically, they can sort of run a single model on a GPU, but they can use, say, 50,000 GPUs at once to get science done. They don't need to actually communicate between them. So it's just one problem on one sort of processor, but they need to run many individual runs of that problem. The other big reason in general why I would say, like, if you haven't done any parallel programming, why you want to be at least somewhat interested in especially if you're doing any sort of scientific or engineering sort of heavy duty math computations, is right, the performance of single traditional CPU cores is diminishing over time, and right, every year the rate of performance increase is lower, and so the only option really to for some problems now is to use multi-core processors, right? So you're only going to get so far if you leave your code in a serial form moving forward. So yeah, what's the solution? So single cores are slowing down, or the rate of their performance increase is slowing down over time. And so, right, over the last 15, 20 years, the multi-core processor is what the solution is essentially, right? So a lot of people still have single core codes, and they have sort of that IceCube problem where they just need to run a bunch of serial jobs over and over and over again against different data, which you can still do in these multi-core processors, of course. But if you have a problem that's serial, now you have a multi-core chip, and so you can start thinking about, okay, how do I take the instructions that I do have in the serial format and break it up into that parallel pipeline in some way, right? And so they have, we have the 4 cores here, just like we had here. So how do you take the original set of instructions and map them onto these 4 physical cores that are now in, say, I think even laptops now are starting to have 4 compute cores on them, right? And things are only getting more complex, right? So this talk was, I think I originally did this, some version of this in 2019. So I haven't necessarily updated these graphs, but you can see here that the numbers of CPU cores on a single processor socket, sort of the package that you would buy in a single unit and put into a system like Expanse, is only increasing. So right, this is the model, right? The single core performance is not improving a ton over time, but the number of cores being put on processor sockets is increasing, right? So on Expanse, ours are 64 core actually, right? And I'm sure they'll, within a year or two, I would not be surprised if there's a 128 core, processor socket. So yeah, this is, yes.
Could you answer? Yeah, there's a question that says, can you explain the difference between physical and logistical logical cores?
Sure. So so the physical cores are, the actual, physical compute, die. This is like a processor die, right? So the core is like one full, central processing unit, in the traditional sense, where it's sort of a general purpose, processor, right? So that's the physical core. The logical cores refer to this technique that's been used for, it's probably been 20, 30 years now at least, or it's probably older, but where basically you're sharing. One of the tricks that processor designers have used over the years is sharing time on CPU cores, right? So essentially, the logical cores, there's something called in the Intel branded version is hyperthreading, right? So if you have hyperthreading turned on say your PC at home or your laptop, even though you might have only 4 physical cores, usually if you have hyperthreading on, it'll say, oh, there's 8 logical cores available, right? And what that means is you set your processor up in this sort of time sharing mode where each core essentially will be able to schedule 2 threads, which we'll talk about in a second here, at once, right? It doesn't mean that you have you don't have the power of the same sort of computing power as you would if you had 8 physical cores. But what it allows you to do for certain problems is sort of slice and dice the time you have available on each core and run different workloads quickly and switch between them. And so it's sort of if one, as you'll see today, if one thread of instructions that are running stops for a bit, your operating system knows that you have hyperthreading on and will schedule that other thread to run on the physical core while the other one's waiting for something to happen, right? Maybe it's trying to find a file and open it and something like that. And so this other thread is going to run on the physical core and do its work while the other one's sort of waiting for something to happen, get something from memory or out of the cache. So it's really this time slicing kind of aspect of sharing the core with 2 different sort of compute workloads, these threads that we'll talk about. So it's a good question. I should probably write that down and put that in a future talk. So yeah, this is the processor. So in addition to this new multi-core world, it's getting even more complicated these days. This is the AMD EPYC 7742. This is the CPU processor we have on the compute partition and the shared partition that we'll use today on Expanse. And what's being shown here is each 64 core processor is actually built out of these 8, what they're calling sort of chiplets now, right? So you actually have kind of in each processor socket, this sort of monolithic thing that you would buy, there's actually little compute core dies that kind of look like this original picture. There's each of those CCDs, they call them, kind of looks like this, where there's cores inside each of these cordoned off sections of these chiplets that are now connected through a communication layer that's on the chip. It's the overall ROM CPU itself, right? And so and within each CCD, there's 2 CCXs, and there's a lot of layers of complexity of shuffling data from sort of memory, the high level sort of DRAM memory on your server down to the individual caches for each core now. So and you do see this complexity when you're running parallel codes and how you want to lay out the number of processors or processes and threads that are running your application if it's able to scale up across all 64 cores on a single processor here. And to add to the complexity, right, this is just one processor. Each Expanse node, compute node, has 2 of these. So right, there's also a PCI sort of communication between sockets now too, that you have to worry about as well. Okay, so I've been using some of these terms already, but just to be clear, because this is going to be very important for what we're talking about today, and kind of if there's two concepts you take away about from today, in addition to sort of the practical stuff of running on Expanse, which we'll do, you'll definitely need to keep these two definitions in mind over the next few weeks as we talk about things in the different parallel computing talks that you'll see. So a process, when we talk about a process, and we're talking here in all of our systems run Linux, so a process or a Linux process is really just an instance of a computer program that's running, right? That's being executed on the system. And we'll use today, if we haven't used it already in the past, Top or HTOP is a program that's available on Expanse in most Linux systems, probably even on your laptops. If you have, say, a Mac, you can run the top command, and it'll show you a layout of all the processes that are currently running, the programs that are running on the system itself, and how much CPU and memory is being used, and gives you all sorts of stats of like how long it's run. But this is like the simplest window into checking of if your program's running and doing some basic understanding of these issues of processes and parallel programming. This is kind of your first debugging tool when you start doing parallel programming, at least it was for me. So you'll see some of that today. But yeah, process is just one instance of your program that's being executed. So if you have some executable and you run it, you'll see that it creates a process by looking at it through Top or HTOP. Right? And then I've been using the word thread, and this is kind of the main topic of today is, what's a thread and sort of how it fits into these parallel programming models for, in this case, we'll do some Fortran and OpenMP and then Python as well. You can think about a thread as just a set of that original schematic. If you break up your problem into those different pipelines, each of those individual pipelines is where you would run your thread a thread is just where those different sets of instructions run, right? So in this case, if you have a serial code, everything's running through this sort of main thread, right? If you're just running on a single core, a single threaded process, that's a serial computation, right? You just have one set of instructions, one pipeline that's being run across the data and the different commands that system calls and all the things that your program is supposed to do. It just does it one after another. When you have this sort of multi-threaded shared memory type of problem where you've been able to break up your problem into a set of instructions that sort of can run somewhat independently, maybe there's some dependencies between them, you can do this multi-threaded or sort of shared memory programming model we'll do today, where you can run these different pipelines in parallel on different compute cores. That's kind of the goal for today, right? So the thread is really just a subset of the instructions from your serial program that are now sort of broken up and can be managed independently, right? And one thing to keep in mind is the operating system controls your threads, right? So once you launch your threads, the operating system figures out when to run them, right? So we had the good question about the physical versus logical cores. That whole hyper-threading thing is, yeah, so when you're sharing time on the same core between two threads, you're not controlling that. It's just happening as the operating system basically decides that they can run separately. Let's see if the chat, is there a question?
Yes, Marty, there was a question.
Yes, memory is shared among threads belong to the same process. Yes, that's another good point. I didn't make that point. So one thing to keep in mind is when you talk about a process, right? A process is also assigned a set of resources, okay? So a thread, yes, threads run in a process, right? So a process is sort of the higher level construct. So when you start your program, it can be single threaded or multi-threaded. but that process is usually assigned some number of compute cores it can run on, right? So you can assign it a single core, you can assign it 4 cores, or however many. And so also same with memory and disk and things like that. But yeah, the simplest thing is think about it is it gets some number of cores assigned to a process and some amount of memory. It's kind of the two to start with there. And then the threads within that can then use however many cores are assigned to the process and how much memory and things like that. But yes, and then the memory is shared. The memory assigned to the process is then shared among the threads, right? Like each thread doesn't have to use the same, say, variables in the memory, but when they start sharing the same variables, that's where it gets complicated, right? Because they are shared in that memory space. Okay, so that's kind of the high-level overview of the concepts. So we're about 30 minutes in, okay. And so what I want to do now is really turn to basically hands-on examples that I'm going to hopefully try to bring you along as fast as I can. We'll see how far we get. But again, like the idea here is not only to show you some examples of processes and threads and the different sort of programming models you can start playing around with these things if you haven't before, but also to get you familiar with Xpanse and make sure you can log in and download the code and get up and running, because you'll do this process probably in the next few talks as well with the other speakers. So this is just a schematic just to give you a logical overview, just so if you're not familiar with Xpanse or running on HPC systems in general, this is kind of just a nice quick overview. So, we're all at home or at work, you have your laptop or desktop, and you're going to connect to Xpanse over the internet, obviously. And where you log in, right, we just call those login nodes. Okay, so they're just a shared set of compute nodes that are available for you to compile programs, transfer data to, maybe do some editing of the files that you'll run today. Some of these batch job scripts we'll talk about. And then, so they're just meant for lightweight sort of work and submitting your jobs to the HPC cluster to Xpanse, right? And once you submit those jobs, they run on the compute nodes, right? And those compute nodes have access to, say, shared file systems. And today we're doing this, shared memory, parallel programming. So all your jobs will run on a single node or less today, mostly less because we don't really have complicated programs to run. We'll just keep it pretty small. But yeah, it's one thing to keep in mind is a lot of these things that you're also touching, like the file systems, so your home file system, it's all actually being done over an internal network too, right? So the shared home directory that you have on Xpanse, it's actually not on the compute node. It's just being served to the compute node to have access to. So there's some complexity to these things that you'll run into if you get enough experience with running on HPC systems. But yeah, this is kind of the framework of the mental model to keep in your head, right? So, and one thing, the reason I brought this up is just, maybe this is obvious, but we also, try not to run things on the login nodes, right? Some people sometimes get confused. They start, running things on the login nodes where you're not really supposed to run computational work, right? Because they're really just for logging in, setting things up, and then launching the jobs onto the system, right? And so that's just the main reason I wanted to throw up this mental model to keep in the back of your mind as we work through today. Okay, let's see, I think, yeah. Okay, so let me go and just post. I'll just post another link to the repo since I uploaded the code that I'll be running. Let's put that in the chat. All right, and yeah, it's week 10 is where the material is going to be. So you'll find the code examples here. I don't know if we'll get to all of them today, but hopefully we'll get through enough material to get you familiar with compiling some of these codes and setting up how to run them on Expanse. And so you can at least play with them after the talk today, if you're interested. Okay, so I'm going to clone the repo to Expanse. So I apologize for those who don't have accounts yet. You won't be able to follow along, but for those that can, I would encourage you to do so. So I'm going to log into Expanse. And so yeah, this is Expanse, right? And we have the Slurm scheduler. Hopefully, well, maybe I shouldn't assume everybody's familiar with the scheduler. Anyway, so the first thing I'm going to do is git clone the repository, because that's where my code is. So it's probably going to take just, hopefully not too long. I didn't actually run a test here. Okay, good. Didn't take too long. Okay, so I'm just going to navigate to the week 10 where my code is at. And we'll set up the first job. So the first example here is very simple, but I wanted to do a simple, embarrassingly parallel job for the first sort of just getting things set up. And it has to do with this bash pi script. So if you, hopefully, I'm assuming people are somewhat familiar with command line editing. So I am a VI user, you might be Emacs user, I don't know. If you're not familiar with text editing on the command line and you're gonna do this type of work long term, definitely get familiar with it. One of them. So I'm just gonna look at my code here, and so this is just a simple bash script actually that computes the value of pi via Monte Carlo method. So I'll show you where you can find how this code is set up and what it's actually doing. You'll see here the important part for us today is you have access to the code, and then there's only 3 input variables that you have to provide that'll run on the command line. That you'll run on the command line. So there's some bytes, there's some rounding setting, and then the number of samples. So if you're not familiar with Monte Carlo, it's one of these problems where you just kind of repeatedly, randomly, throw some dice essentially and get some random variable to solve the problem. And so that's what these numbers of samples are. The bytes and rounding just has to do with like the format of the data and sort of, you can kind of see the size of the integers you're using and things like that. It's not too important, but we're going to use this to set up a job. So this is just a serial code, right? So again, when we're talking about parallel programming, for some problems, you might not really need a shared memory programming model necessarily. You might just need to run a large number of individual serial jobs for your work, right? And get all those outputs, and then maybe compile the results from those simulations. Like this is a very simple simulation computing the value of pi, essentially. And you could combine all of those results from each individual run that we'll do here. If it's just not really that interesting. We know the value of pi pretty well, but this is just a nice exercise. So you can see it's just there's an if statement, there's a for loop where you start running over how many samples you want to run. You just compute some final number of pi over all of the sort of, after all of the runs are done and all the samples have been taken for this individual job. And just output will be the value of pi that it's estimated, right? Now, to run this, right, we could run it on the login node, but we don't want to do that. So to run these jobs, right, we set them up in batch job scripts, right? And so we'll do that now. And so if you're following along, what I usually do is just type I just create a new file with the same name of the code I'm going to run. But I just say run as run, put it like a run prefix out in front of the new script that I'm creating. And usually, start a new script with something like this. So here I'm just saying, starting a new bash shell script. If you're using a different shell, feel free to change things up. I think by default, all of the users on Expanse are bash users. So this first line just makes sure that, essentially, the shell knows it's a bash script. It's not too important, but when you're doing editing and things like that in, say, VI, the extension here is helpful because there's syntax highlighting. You can kind of see that there's different syntax highlighted because it's a bash script. I also have at the top here the same thing. So it's just kind of a hint to VI as well here for the syntax highlighting. Okay, so if you haven't written a batch job script or haven't ran anything on Expanse yet, so there's the Slurm scheduler is used on Expanse. And what you do at the beginning of any of these batch job scripts is you just have to provide a set of directives, basically it'll kind of look like comments that the scheduler can read and interpret as, these are variables assigned to your job. And essentially you're asking the scheduler to take the code that we'll put here, the commands that we'll put later, and we want to run them on one of the compute nodes out on Expanse, right? And so you have to specify, the number of resources you want, how many compute cores, how much memory, how long you want the job to run, and a few other ancillary things we'll throw in here, okay? So I'm just going to walk through kind of the very basic ones that I always put in for any job. And so the first one is just the job name. And we'll just do bash PyTest. Okay. And sbatch. The next one is we have to charge the job to a certain account, right? So for those who don't have accounts yet, once you do have an account, what'll happen is Mary, who's the organizer of the training series here, we have an allocation of time for the students in the training series. And so that's sort of what you'll put here on this next line to basically every job you run on Expanse, you have to charge the job to some sort of allocated amount of time for the project that you're on. So let's go ahead and check what the account is, because I forget. To do that, you'll just do a module load Expanse client. Oh, no, sorry. Module load SDSC. This is just a software module that we have on Expanse that has this Expanse client tool in it. And you'll just do Expanse client user, and it lists all the projects you're on. And I believe it's, well, it's going to be this one for today, because is that the right one? Mahi, do you know?
Let me.
Because for some reason my other ones are zeroed. I know it's not that one. I know it's not that one. I know it's not that one.
So yeah, that looks like a training one. Let me just double check.
Okay, I can check here. I think I have. Let's see. I'm not logged in. I feel like it's the CCR one though.
Marty, it's the TRA.
Okay, TRA.
Yeah, that's the one. That's got Mary as the PI, so I think that's the one.
And that's for the training series.
Yeah.
Okay.
Oh,
Okay.
actually, no, that looks like a CINL one.
Yeah, I think this one is for Simul and this one is for the training series. So for some reason, I don't have any time. I know it was renewed recently. We'll have to check. If anybody who's on the allocation can check if they have time, that would be good to confirm too.
Yeah, it's the CCR 190013.
Okay.
That's the
Okay.
training one.
Okay, Eckhart, thanks. What's your username? Okay, so Billy has 500 units. As long as you all have some units, I guess I didn't ask Nicole to put some units on mine. I think we recently, I think the allocation recently got renewed and we probably sliced it up again for the students.
Yeah, so so the users can, I mean, the students can use the STS 173.
Yeah, let me do this. I'm just forgetting my Expanse clients options. I can check the project, right? The project details.
And now you got a typo in the Expanse.
Yep. I should be able to see. Is it project?
Yeah, just give it the name, whatever.
Oh, yeah. Sure.
Yeah, so you can
Okay,
see.
yeah, okay. So hopefully if you have an active account and you're here and you should have some time. It's just mine that doesn't for some reason. Anyway, that's fine. So yeah, it's SDSC 13 would be your accounts here if you're creating your batch job trip. You can also, as Bart pointed out, you can also use the longer format, exceed allocation ID, that TG dash larger project name. You can also use that there. The shorter ones are just the local SDSC project IDs. So I'm going to use my one for our group, just the use 300. But please put yours in there, otherwise your job won't run. Okay, so the accounting, so you need to always run your jobs charged to the SDS 173 allocation. And so the next line is, since we're running on a single node today, we're going to have one node. Actually, I usually put next the partition. So this partition variable is where the job will run, controls what compute resources the job will run on. And today we're going to use the shared partition. So this will make the job run on these AMD EPYC compute nodes that I was telling you about. The shared partition here simply lets you run jobs on a subset of the cores on the node, right? So you don't need to run on the full node with all 128 cores that are available. We're just going to do some simple tests today, and up to maybe 4 cores or something like that. We'll request. Okay, so we're going to run the shared partition. The next thing is n tasks per node. I'm going to do just 1 for now. All right. Because we have a serial code, CPUs per task. Just I'm gonna ask for 1 CPU. Mem, I'm gonna just stay at 1 GB. So this is the default. So I'm just putting it here explicitly. For every CPU core that you request, you get assigned by default 1 GB. I'm just gonna put it in here to be explicit, so you can play around with these settings later for different types of problems. Okay, so we have nodes, the number of tasks or processes, essentially. You can think about the n task per node is the number of processes you want to start, right? On then however many CPUs and how many cores do you want assigned to that process, as I was discussing. Okay, and then next, I think we just need how long our job is going to run. So let's do just sort of hours, minutes, seconds format. We'll just do 5 minutes for now, because we have very, well, I don't know exactly. I should have tested how long. Oh, we'll do a small problem. You can play around with the time later, but you can adjust the time settings, and then an output. And the output, I just do %x.0.j. So this is just where the standard output file will go. So remember the bash pi script at the end, it's just going to print out the estimate of pi. And so that's all that's going to be, I think, probably written out. Well, maybe a few other things will be written out to the output file. But basically this last line here just sets up the output file that the scheduler will dump the standard output from your program to. And basically this sort of weird looking configuration here of these different variables is just this %x is place the job name there. I just say, I label it with an O for output. This %j is the job number, you'll see. So every job is assigned a number. And this capital N is just what node did it run on, right? So you'll see that, what node your job ran on. The next thing is, I think for all of the examples today, we don't really need any of the fancier versions of the software that are available in this software module environment that I mentioned briefly. So the first thing I'm going to put here is a module purge. And so this is just going to, we're only going to be running with basically the native system software today. We don't need anything more, more involved. So we'll just clear everything from our software environment and then run the job. And I'm going to do something here. I'm going to do this time -p command. And this is just going to set up a simple timer. So it'll tell us how long the job took to run in the output, right? And so I'm going to do a bash pi shell, and we had 3 different command line variables. There was -b for bytes. I think 8 is a good setting. The next was, what was it? The rounding, R. I think 5 is a good number. And then the samples is what's really going to change a lot of the time. And we'll just do 1,000. I think that'll finish within 5 minutes pretty easily. And I believe that should run. Okay. Oh, one thing that we didn't do. So that's hopefully, I'll just put this in the, I can probably copy and paste this for anybody who needs some help. That's my batch job script. So this is what you'll be seeing examples of. I didn't create an example today because I wanted to sort of reteach people like what we're doing here when we're, so you know how to adjust the different options as you work through some of the examples on your own. For example, like the most complicated one at the end of the day will sort of be the take-home homework. You can adjust, how many cores you want, how much memory you need, because it all depends on the problem size you're doing and things like that. So it'll be kind of interesting if you go into those details. Okay, so that's a simple batch job script for this bash pi. And now we want to run the job. There's one thing that we need to do. Let's just do the, well, I forget, do I need to? Anyway, I'm just going to do it just in case. So I ran this command just to make bash pi shell script executable. You'll see the color change. This just has to do with the Linux permissions. I actually don't think I need it with the ./, but I'll just do it for saving time so we don't get a failed job. Now, once you have your batch job script ready to go to run the job, you will submit it to the scheduler, right? So this is the sbatch command. So you type sbatch and the name of your batch job script. And you see that it was assigned a job ID, as I mentioned, And now to check the status of the job and see if it's running or if it's waiting to run, you use the SQ command. And usually you want to do the SQ command with your username so you don't see everybody else's job. Of course, it might have ran too fast. So let's see. Yep, it looks like it already ran. You can see here, there's an output file that's now available from with that format that I mentioned, the name of the file. I put a O for output, job number, and the node it ran on. So you can kind of just look at the output. It has an estimate of pi. And then these other 3 lines are from that time p command. Basically, the one that I usually just look at is this real. This is sort of, it ran for 7 seconds, right? In this time format that I have set up. So the time p, this is going to be how many seconds that command that wrapped, right? That we did time p, it's sort of wrapping this whole command, right? So it's timing how long it took for that command to run. So let's just crank this up one more, maybe 10,000. See if we can just do another quick example. This batch. And you'll see if you play around with this code, as you ramp up the number of samples, the better the estimate of pi should get. It'll also take longer to run, obviously, because then the loop is longer. Okay, I don't know how long this is going to take, but probably 10 times as long, so maybe a minute. One thing that I'll point out while we're waiting here is one thing that you'll be doing when you're doing parallel programming and running things on HPC systems is you'll want to check if it's actually running sometimes. And on Expanse, what you can do is you can SSH directly to the compute node that you have access to. And you can run this top command that I was mentioning. So you can run top in your username. And here we see a bash command that's running on 10% of the CPU that we have. We have one CPU core. It's using 10% roughly of the compute load, or the compute power. And that's probably where our bash pi, that's our bash pi process, right? I mentioned that using this top command will show you what processes are running, right? I used top -u with my username. So only the processes that are assigned to me running on the system, right? So that's how you can do a quick look at the process you're running. You see here that if you are logged into the node while your job is running and you're looking around at the node, once the job ends, you'll be kicked out of the node because you no longer have access to it. So that's what happened to me. You see here with the connection expired or connection closed by remote host. That's all that happened. So we can look at the outputs. We now have a second job that ran. Look at the outputs. You can see the estimates a little bit better with more samples. And again, it ran about, we increased the number of samples by about a factor of 10, and it ran about 10 times the time, right? It was about 7 seconds for the 1,000 samples. For the 10,000 samples, about a minute. So that's a very simple job, right? Now, like a lot of different Monte Carlo problems, well, this is kind of a toy problem, right? You generally don't necessarily need to run a huge parallel simulation across a 2-socket 128 core node. Sometimes you just need a few cores, or you need to say run. Not only do we want to run 10,000 samples in an individual job, but maybe we want to run 10,000 jobs across the entire Expanse system, right? Expanse I think has upwards of almost 100,000 cores. So in theory, you can run 100,000 of these simultaneously across the system, right? Now we're not going to do that, but to kick off, now that we know how to submit jobs, we've run a simple serial job. The next thing is, well, this is kind of one of those problems where if you just need to do an independent simulation, how do you do it? It could be an embarrassingly parallel job where if you wanted to take many samples of this same program executed over and over again and combine the results of those pi estimates, you would then get maybe a more precise estimate, right? Now it's kind of a simple example, but how do you do that? How do you run an embarrassingly parallel job like that? Well, the nice thing about the Slurm scheduler here is there's a very simple way to take the simple batch job script that we just ran for this bash pi program and turn it into an embarrassingly parallel workload, right? And run multiple copies of the same job on different cores on the system. And then the Slurm scheduler will actually manage those jobs being run and the output that's generated, right? And so what we'll do is make a copy of this batch job. So we'll do a copy, run bash pi array. Right, so I'm just going to make a copy of our batch job script and make some edits here. And what I'm setting up here is an array job. So it's very simple. I'm going to change a few things here. So instead of the %j, I'm going to do %small a, I believe, and capital %a. So you can definitely look up the documentation if you're interested. And so what these Slurm job arrays are is it allows you to submit a single batch job script like this to run multiple copies of the same job with maybe slightly different parameters, right? So if you wanted to run, I mean, this is a toy problem, but it gives you hooks into being able to set up multiple versions of the same job with slightly different parameters. Or say, for example, a good example here would be like if I had a seed variable where, it would start, the random seed would be slightly different, which maybe I should add that to the program eventually, but I don't have one right now. So this %a and small a and capital A are just a different format of the job number. So now in the job array, what you'll have is you'll have the sort of same, what's 8, 9, 10 digit, I forget how big the job IDs are right now, large number. And then you have not only the sort of array job ID, but you have individual tasks in the array. So the sort of sub jobs that are going to get run. And how you ask for how many you want is you give a range of the number of jobs that you want run. So I'm just going to say 1 to 10. So I'm going to run 10 different versions of this same calculation in this embarrassingly parallel format, right? I've changed nothing about what I'm running. Each individual job is going to have different random numbers, right, in each simulation. So each bash pi calculation, right, it's essentially running this simulation to calculate pi, and you'll see that the results are different, like in these individual jobs. And we're just going to run again this simple single core simulation, but we're going to run it 10 times and get slightly different results because maybe that's what our science needs. And this is what we would say is an embarrassingly parallel kind of job, right? Where essentially we're just working on different data in independent ways and getting, results out that will then, further our science or engineering case or whatever research we're doing. Okay, so if I do a sbatch run pi array and submit it, you'll see it creates 10 different jobs. So we have this very, again, embarrassingly parallel workflow going. And if we want to log in somewhere again, just to then see here, we should probably see if we look, we have 3 of the array jobs or sub jobs are on Expanse 01. So we should see like at least 3 kind of beefy bash scripts that are running. These are the 3 jobs. So those are the 3 independent processes, right? These independent versions of the program that are running that were assigned by the Slurm scheduler to run that array job on this node. So there was 3 assigned to this node. You can see that they're all running here, right? And that you can see how many compute resources they're using. So it's not much, right? Okay, so that's a simple array job. So if you're, the kind of work you're doing can benefit from that this is kind of like one of the easiest wins in sort of the parallel computing space, right? Where you just need to run a lot of copies of the same thing. This is that throughput job, right? It's not, we're not speeding up the job. We're not scaling up the job. We're just want to run a lot more versions of the job more quickly, right? So it's sort of more of a holistic system-wide approach to the problem here. Okay, so now we should see that we have a bunch of output from the array job. We see, again, I got the format backwards. That's okay. So you see here, here's the job ID for the array. I got the capital A is the big job ID. I should have remembered that. And then the individual jobs have a task ID, so an array of task ID. So each individual subjob has its 1 through 10 setting. Now on an Expanse, I wouldn't go more above 10, right? Again, we're using up compute time when we run these things, just to note a limitation, right? I think on Expanse we limit the number of array jobs to 1,000. So, or the number of tasks or subjobs you can have are 1,000. So any range, I think any range of values works here as long as it's within 1,000. So if you need to move the numbers around, I think that's a true statement. I haven't tested in a while, but I think that's true. But yeah, you can only run 1,000 in a given submission. And they won't necessarily all start at the same time, right? So if you have, really computationally heavy jobs in the array, maybe some will start and then, you'll use up enough resources that you can't, get any more, because, we ran on a single core, but, the array job could be each individual sub job of the array could be assigned to a whole compute node. Right? Okay, so that's the embarrassingly parallel kind of example I want to show today. So the next thing, let me just clean up the code here. Let's see. I don't think I need this anymore. Move this out of the way, kind of. So I'm just going to clean up my folder here a bit and move on to the next. So I just deleted my output files basically. To the next example. So the next set of examples I'll show you is the basic sort of initial sort of OpenMP hello world. Okay. Now in the code folder here, you have a make file. So a make file is just a set of instructions to compile the programs. And so we can look at this here. So, okay, I think oops, sorry, my make file is a little off. That's okay. It didn't include the C versions of the program here. I'm just seeing that here. I'm just modifying it slightly. There's an errant hello C in this first line. So you see here, basically what we're going to be using is some simple Fortran codes. I'm a Fortran programmer by training, so I just sort of still more comfortable just doing simple things in Fortran even. And I think it's, for teaching purposes, it's much more easy on the eyes for people, even if you're not familiar with Fortran. You'll be able to get what's going on versus a lot of the sort of more minutia of C's syntax. If you just, and basically, I'm assuming that no one is necessarily a C or a Fortran programmer, and so I just want to go with like the simplest thing in terms of teaching you guys today. And yeah, so we have this make file. Basically, there's 4 different programs in here. So there's this hello world examples. We'll do the hello world and then the hello world OpenMP. And then there's a matrix vector one that'll probably be take home since we only have about 45 minutes left. But that's where we're kind of the last problem. But this Makefile will help you compile all of them. To do the compilation, you'll see if we do a module, I'll just do like we had in the batch job script, I'll just do a module purge. There's basically a Fortran compiler on the system by default. So you can see there's a G-Fortran, there's a GCC. If you have a C code that you want to compile, you can use this. This is not what we recommend people use for sort of, you know, if you're compiling like a real sort of production workload application. But for today's examples, this is more than enough just to use the system version of the GCC compiler suite. And we'll use the G-Fortran 8.5 here. So to use the Makefile, all you have to do to compile, say, the hello world code is do make hello, right? And it'll run that line that was in the Makefile, right? And so what we get out is basically we're taking this hello world code, this hello.f90. Looks pretty simple. There's just a few lines. You know, not too many, you really get into the program details, but basically this is the only meaningful line in the code that you care about today. So we're just writing back hello world, obviously. And you know, I'll do the bad thing and run the code on the login node. It just runs hello world. Okay, but of course we're going to want to set up a batch job scripts for these other problems. So I'll just set one up for the hello world case too as well. Yeah, we'll just copy the run batch py to run hello.shell. It'll look very similar. It's just we'll do hello test. Okay, that's again just single core job. You can run it, run hello. So that's one thing you've the module purge. So the slurm commands you still need. Control load slurm. Sorry. Okay, so we submit our hello world. It's probably not going to be very interesting, obviously. It's very fast. So test hello world. Okay. Now, the first, so again, just to come to OpenMP and just mention kind of what we're doing here. So again, we have this serial program that we have, you know, obviously this one's very simple, but you might have some other serial code that's written in Fortran or C. A lot of scientific and engineering codes are written in Fortran C that you might be using, maybe if you're graduate students or undergrad doing some research with a professor at UCSD or a different campus. You know, they might have had some Fortran or C code for their projects that's been, been used for many, many years. And, maybe it's just serial and they still use it. You can try to parallelize it with OpenMP. And so I'll just also point back to the slides quickly before we jump in here. At the end of the slides, there's a few references. And so you'll see some of the stuff that I've stolen for the schematics come from this Introduction to Parallel Computing tutorial from Lawrence Livermore. I can't really do a better job than some of these like online tutorials from Lawrence Livermore. They're really good. They've been around forever. I think I learned off of them when I learned parallel programming for the first time. So I would highly encourage you to go to these links and check out the these parallel programming and computing tutorials. And there's the OpenMP one as well. So if you really do want to get into some of the details of what's going on in these OpenMP examples and the constructs and things that are being used. There's a lot of information here. Again, like I mentioned, this could be a semester-long class itself, probably. But again, so OpenMP, what is it, right? It's an API essentially. It's directive-based. I'll show you what directive is in a second. For this sort of multi-threaded shared memory parallel programming model, right? For C and Fortran codes, and so you can kind of see all the details of what it's for, what it's not for, sort of the goals of why OpenMP was invented, I think in sort of the late 90s. And even today, it's really advanced. Like, right, there's now support for like GPUs and stuff, I think. So there's a lot you can do with it. But just learning the basics and getting up and running on simple stuff it happens pretty quickly. But there's a whole other set of things with, getting around things like race conditions we'll see here in a second, and deadlocks and stuff. It is, yeah, there's a lot you can learn. I'm not an expert by any means. But yeah, this is a very nice tutorial, walks you through some of the history and things, and then goes in through all the different sort of formats of C versus Fortran, the different constructs you'll see, the parallel construct, which I'll show you here in a second, and then the Hello World example. So there's all sorts of stuff. There's exercises you can do. If you really want to get into this and you are familiar with C or Fortran, this is where I would go to sort of walk through some more examples and sort of some of the details that I just don't have time to touch on today. Okay, so the whole idea though is you have a simple serial program in C or Fortran and you want to parallelize it. And I gave you a simple Hello World example here. If you haven't looked at it yet, it's the hello-OpenMP or OMP. It's kind of usually the short acronym for it. And you can see how things change, right, from one program to the next, right? So there's, instead of one meaningful line, there's now a few different meaningful lines, right? So we have some variables here that we've set up, some integer variables to sort of store the number of threads that our program runs on. We'll also, each thread usually has a ID associated, kind of like the jobs we just ran through the scheduler get scheduled, right? Threads have IDs as well. Processors have IDs. If you look at the top program, right? PID, processor ID. We also have thread IDs, right? So that's important concept to keep in mind, right? Because again, Slurm schedules your jobs and has an ID, the operating system will schedule what threads are run, right? And the processes, so they keep track of things through IDs. There is in OpenMP, you'll see very quickly when you get started with it, there's different sort of built-in functions that get you information about your OpenMP environment when you start up a job. And two of the most important things are sort of this OpenMP get num, basically you ask OpenMP to tell you how many threads you have access to, or what your thread number is to get the ID of the job. And so that's what those variables are for. Now, the next part is really what OpenMP programming looks like in sort of the most basic generic format here, right? So the basic sort of abstraction is using these directives, right? So if you're familiar with Fortran, exclamation mark like this and these first 6 lines are all about creating comments, right? So this creates a comment. So just like the S-batch comments in your batch job script tell Slurm about how to run your job and what resources you need, these directives from OpenMP tell the OpenMP library and your compiler of how, and the whole runtime, how to run your parallel program, right? And the basic setup is you start a parallel section in your code. So once you you know, it's not, it's all a manual process, right? So you remember you had this serial program with a set of instructions. You have to figure out how you can break up that set of serial instructions for your job into a set of parallel tasks that can be run on different threads in a safe way, in a meaningful way, right? So all you have to do though is in your serial code, start putting in these directives and create this first one is a parallel section, right? And within that parallel section, you can have multiple threads, right? And you can, how many threads you set, there's all sorts of ways you can think about it. Specifying it. Here, I'm doing it somewhat implicitly. I am not assigning anything to the parallel section in the code, right? So I'll show you, you set that at runtime using some environment variables usually. This OpenMP num threads environment variable. I'll show you when we create the first job here. The second part here of this parallel construct is private. This has to do with the memory management thing. You have to sort of manage your variables, right? Here, I've set the thread ID to be private. Why is that? Well, each thread will have a different ID, and you don't want every thread writing to the same part of memory. And so you need multiple copies of this thread ID variable that each individual thread can write to in the parallel section, right? So hopefully that makes sense. Okay. So what we're doing is just, we're in this example, very simple. We're creating a parallel section. There's going to be multiple threads run. Each thread will get its own ID with this get openmp get thread num section. It'll then, well, this simply says if you're the main process, tell us how many, this basically says only this master or main process will run this command, right? So the original thread of the program that started up here is this, what they call the master thread in OpenMP. And that's, this section here just says only that thread will run this command, right? This barrier command is to synchronize things. So basically it's kind of like a wait. So wait for all of the threads to get to this point in the code. And then once everybody knows their thread ID and the master thread knows not only its ID, but how many threads we are composed of, then each thread will write out hello world, right? So hello to the shared memory world from which ID and how for, of the total, right? And then you end the parallel section and then the program stops, right? So basically it's what we call this fork and joining model that is discussed in this Lawrence Livermore tutorial, right? Where basically you have a single process thread, process and thread. Here you split that that process. You still have a single process, but then you spawn multiple threads and you fork that main master thread into multiple worker threads. They do some work and then you bring them back together and then carry on with the next, say, set of serial commands down here, or in this case, we just end the program. Okay. All right. So
There's a question in the.
Okay. Question. Is OpenMP get thread num a local? Yeah, so that's so the OpenMP get thread num is actually a function, right? So it's a function. It's sort of one of these utility functions in OpenMP to get the thread ID, right? What we've done is create a private version of the thread ID variable. So this is, you can consider this thread ID, anything that's in private is local to an individual thread. Yeah. Okay, so to compile this example, you just use the makefile and hello OpenMP. Right, so we'll have the hello OpenMP example. I'll do a copy of the batch job script. Okay, we'll just do some quick modifications here just to keep things organized. And we're going to run the hello OpenMP code. Now, I'll run this as it is right now. I'll submit that job. See what happens. It ran pretty quick. Check the output. So what do we see here? Okay, so we see that it printed out hello shared memory world from thread 0 of 1. So what does that mean, right? So here I just ran the executable as it was compiled, and very similar to how we ran the original hello world. But what do we see here? Well, the first thing that's printed in the sentence here, the variables, right? This was the thread ID. So the thread IDs are numbered from starting from 0, you can see, right? And the total number of threads is 1. So there's only one thread of ID 0 in the job that we ran, right? So, okay, how do we run on multiple threads then, right? How do we have multiple threads run? Well, we'll go back to the job, and you'll include one environment variable, export OMP num threads. Okay, so this is effectively what we ran, right? Is we had a single thread run the code, so that's why they only ran with one line. If you want to increase the number of threads, all you do is you change this environment variable, right? So we'll do 2 and rerun it. I should just assume it's running too quickly. All right, so we ran our second test with 2 threads this time. So we should see 2 print statements, right? One from each thread with different IDs. And that's what we see, right? So again, very simple example, but you know, you can see the complexity starts increasing. You know, we went from basically 1 line to, I don't know, 10 lines or so, just to do a hello world, right? So you can see things can get much more complicated quickly, depending on what you do. And, you know, if you look at the parallel construct in the, you know, there's all sorts of options that you can add on and tack on here, right? You can make a list of the shared variables by, you know, there's all sorts of things with first private versus private. There's a lot of nuance here of things. And again, you can even explicitly set the number of threads that are run in a parallel construct. So there's a lot of nuance here. You can even have like conditions of if the parallel region runs, right? So there's a lot of things you can do. This is kind of, again, the simplest. And we just don't have a lot of time to get into all the complexities here. Let me see what I want to do. We have about, say, 20 minutes. I'll try to do before we stop because we're running a little bit long here. The one thing that I'll mention here before I move on, because I don't think I have time to get back to it, is there is this more complicated OpenMP example in the Makefile that I mentioned. And this will be like take-home homework. There's a few slides on what the problem is that's being solved here that you can play around with. And it's just a simple matrix vector multiplication with a specific matrix. It's easy to check the answer essentially. And so again, just like the Makefile, you can, I would inspect. I think I commented this stuff pretty well in the past, just for people to take home of what's going on here and how to run things. Again, you'll compile it. You can see I just do the time p matvec with the size of the problem here of the matrix, and It's commented pretty well. You can kind of see what's going on. This is the serial version of the code. It's all in Fortran, but hopefully you can kind of follow what's going on, you know, allocating memory here and setting up this vector in, or this, you know, matrix. And then there's the OpenMP version, right? And again, here you can kind of see that, you know, now you also can set not only the size of the problem, but the number of threads that are used to compute the problem. So this is a good test problem for sort of exploring, if you were there for Bob's talk in the first half of the training series. You know, he did this examples of plotting parallel scalability and on graphs from data that you collect for how long, say, it took to run a problem of a given size, right? You can do that with this example because it'll crunch away on some numbers if you really put a decent sized problem in there. And you can then, again, it's the OpenMP used here is very simple. It's not anything complicated. This is kind of the second thing you learn in OpenMP is how to do like in Fortran, it's a do loop. In C, it's a for loop, right? So you can basically, obviously, this is a very simple example, but you just we're creating this array or this vector, and we're just setting every element of that array to 1. Well, that's a very independent thing you can do, right? Every individual element in that array doesn't need to be separate CPUs can assign that variable to that other part of memory, right? So one of the very simple constructs that you start off with is just parallelizing loops, which is kind of the most common thing you do. And this is what's done here to do this sort of manual matrix vector multiplication. Yes, good question, Caroline. I was just going to mention that. That's why I kind of wanted to go to this quick overview of this example you can run later and take home and really crunch away at how the problem size and the number of threads you assign to it change the runtime, right? Because this is you know, the bash pi embarrassing parallel problem was that throughput problem. This kind of simple example is really tackling that speed up problem, right? We want to solve the same problem faster, or I want to solve a larger problem faster, right? You can play around with that speed and scalability issue here in a very simple way. Now, yeah, that's a good question. So the question is, okay, I'll just use my hello world example here. Oh, someone. Oh, come on. Oop, I won't get the batch script. Okay, so one thing that I kind of hid for a second is, right, I ran with 2 threads, but I didn't request. So Carolina's problem is asking essentially, yes, in this case, for example, I ran on 2 threads, but I didn't ask for any more cores, right? And so when you do get to running that matrix vector code, matrix vector multiplication code, you're gonna need actual cores, right? Obviously running a hello world program, I don't really need more cores. It just kind of looks like it's running in parallel, but to actually physically run in parallel, yes, you would want to say if we wanted to run on 2 cores and 2 threads and have those threads get assigned to the different cores, you would want to request 2 CPUs for your single process that gets started. Right? Yeah, so Sinclair, yeah, the job charging, yeah, running short jobs, it does round up. The minimum run time that we charge for is 1 core hour, right? So that's what Mahi is saying there, 1 SU. So yeah, if you're gonna, you know, eat up your SUs, don't run too many of the hello worlds, just do a few and then stop. Because yeah, it'll just start, you know, ticking away at your 500 SUs. We can always backfill you because we know the time's not actually getting used, but it's just it takes time for us to backfill you. So try to save your time for the beefier calculations, for the matrix vector stuff. Okay, so I'll leave that as homework. You can take that home, but you know how, the make file's there. You have the example job script with the hello world. You just need to plug in now the matrix vector one, and hopefully it's documented well enough. All right, so for this last 10 minutes or so before I kind of stop and open up for any discussion or questions at the end, for Python programmers, I kind of wanted to, I'm kind of newer to Python. I would probably say my second language now that I'm fairly comfortable with, and a lot of people doing stuff on Expanse these days, all sorts of different, across all the sort of science, engineering, and whatever research disciplines are doing computational analysis on Expanse or simulations. Python's a big thing for very popular across all disciplines, especially with like machine learning and stuff. Things like TensorFlow and PyTorch are all sort of most commonly used through their Python APIs. And so I kind of wanted to get some flavor of Python examples in here as well. If some people who are probably more familiar with Python than I am, there's all sorts of math libraries like NumPy and stuff like that. I don't have any examples here, but I did work through a pretty nice tutorial that is also referenced in the slides. And I'll point out essentially these threading on the threading library. So it's a very nice tutorial. I mean, it'll take you probably a couple hours to work through it. It did for me at least, just to get familiar with the threading library. But I included some of those examples in the code base here. And so again, it kind of starts off where we did, what's a thread? And there's actually different types of threads in Python, these daemon threads or non-daemon threads. But there's nice few set of examples here. And I think I go everything through the basic synchronization using a lock. Now, this is a very different sort of mindset in the tutorial of running threads than say traditional sort of OpenMP, where it's usually sort of more computational focused. This is more focusing on dividing up, the problem of really dividing up those instructions, right? You have a serial program, but you can then, fork sort of those set of instructions into different threads to do different work, right? And it's really, these examples really just play around with the basic mechanics of getting started with the threading library in Python. So let me just clean up my directory here a bit. So you'll see these Python examples. And the first one is just the two threads example. So they don't really have names for the code in the tutorial slide, or the tutorial there that you'll find. But again, the URL is just here. And it's all really about this threading library. And it's fairly straightforward. Even if you're not familiar with Python, I think you'll be able to follow and play around with it. If you're not familiar with Python, I would also highly recommend. It's a nice language. I like it a lot. And again, for teaching purposes, it's very easy to read. Here, it's a little bit, it's more difficult than it needs to be, but they do use this logging library. If you're not familiar with the logging module in Python in the standard library, it's pretty useful. It's the fancy version of print, basically. You have different logging levels, and you'll see that as you work through, and it's kind of nice. So I left it in. And it looks makes things a little bit more messy, but it's not too bad. And if you're a Python programmer, maybe it'll teach you something if you're not familiar with the logging library. So this is just a very simple Python program that's essentially like a hello world, but it just sleeps. So it basically starts a thread, right? So it basically creates a thread from this threading library. So it creates a thread object. and you then start the thread. The thread, what does it do? Well, the thread runs a function that we defined up here, and all our thread function does is basically print something, sleep, and then say, oh, I'm done, and that's it. And there's a few things in here like the join, where you can actually, force the join of the threads back together because you have a main thread always, and then you fork it off into this side thread here. It's a nice example. And just to save time here at the end, I'll just do a few examples on the login node since they're not very heavy, right? So there's, again, just like the Fortran examples, you can just use the system Python. These aren't complicated, but they're nice, just exercises. So here I'm running 2 threads. What you see again is just creating a thread. In the main one, you start the tasks. The main thread is then waiting for those thread tasks to complete. But you'll see here, they walk through some nice logic, right? You can see here, it says that the main program completed before the thread that was created completed, right? And that's because of this join statement that was in the example, right? So there is a manual process for controlling when these things come back together, or whether or not the main thread waits around for, say, a thread it created to complete, right? So there's all sorts of nice logical sort of exercises that you can walk through and get familiar with some of these different methods, right? The start method, the join method. Now, if I use the join method on my thread, what happens, right? The main thread will actually wait for the thread to complete before carrying on with itself, right? It's kind of like that barrier statement that was in the OpenMP example for the hello world, right? There's all this issues about synchronization of threads, right? I forked off this one thread to go do something. It's just a sleep statement, but do I want my main thread to wait around for that to complete or not, right? These are questions that you have to keep in mind when you're doing not only shared memory or parallel programming, but I'm sure Mahi will have in some of his examples. There's always when you're doing parallelization, there's a lot of this question of when do you synchronize things, or when do things need to be synchronized across the processes or threads that you're running, right? So I would highly encourage anyone interested in Python stuff to walk through this. The examples are already here for some of them. The thread pool is kind of just a simpler way to use, or not simpler, kind of the more correct way to do things. It simplifies the coding with instead of doing this, start each individual thread manually and join them. There's all sorts of different constructs that the Python standard library has built in from this this threading functionality to run things. Now, the one thing I'll say before we wrap up is, right, I think this walking through this threading functionality is very useful in Python. For like scientific computing, the threading library isn't super helpful, I think. And this gets into some issues with how Python works with there's a sort of, as you'll see here, there's an example for a lock function. Oh, yeah, there's the lock. A locking mechanism to control this concurrency and parallel, threads running in process. There's this whole issue about locking, and Python essentially has this sort of mechanism of how it controls threads by default, and it's not really great for using threads as your parallelization mechanism for sort of computationally heavy work. But there's also the Python multiprocessing. So for process-based parallelism. So there's the thread-based parallelism in Python, but there's also the multiprocessing. This is what's more typically used for more, as they say here, sidestepping the global interpreter lock. This is what I'm mentioning is sort of limiting to threading in Python, depending on what you're doing. But I think this tutorial is a really nice place to start. I'm sorry I didn't have time to sort of walk through it with you guys here, but it's really well written, and I would definitely at least get down to say this deadlock one. This producer consumer one gets a little bit more complicated, but the learning how to understand how to create or what a deadlock is something that's useful also in the OpenMP program world. Like you can, these same sort of mental exercises that you work through here in this Python one are problems that you also encounter in OpenMP programming as well. So it's kind of a nice way to tie the two things together. There really is just general concepts from both the sort of more traditional OpenMP shared memory programming model for scientific computing codes, but you'll see a lot of the same concepts that are important in both to keep in mind when you get started with parallel programming. And that's where I think I will stop. Let me just go back to the slides, see if I missed anything. I don't think so. Again, this explains the matrix vector problem and gives you some, parameters to use, and I think that's it. Yeah. So I'll stop there for any questions, I think. All right. So I think, yeah, let me just go to the webpage. So next week, I believe, is Mahidar and MPI, where he'll talk about distributed parallel programming. Yeah, week 11. So introduction to MPI. So there's also, if you go to the Lawrence Livermore labs, they also have a nice MPI tutorial as well, which will probably cover, again, like my talk, cover more details than maybe Mahi will get to, but just another, he'll probably have that reference as well. So, but if you want to read up on what MPI is and how it's different from OpenMP before next week, this is where I would start. All right. If there's no other questions, Cindy, I guess we should stop recording and just see people next week. If there's, do you have any other announcements?
Nope, I think that's it. Just we hope to see you next week, and keep an eye out for my wonderful reminders.
All right.
Thanks, everybody.
All right. Thanks, Cindy.
Thank you, Marty.